I believe we're recording, so I think we should welcome everybody to the Metaheuristics stream. I'm Andrew, just checking you can hear. Enda, we're also doing with Enda.
Hello, my name is Ender Oskamp.
I'm Andrew Parks. We're from University of Nottingham, organizing this stream of an hour long. We're both academics, the University of Nottingham, in the COL research group, Computational Optimization and Learning, School of Computer Science, University of Nottingham. And we have two talks today, as you see on the screen. First talk, solving very large vehicle routing problems with the help of machine learning. Second talk, new metaheuristic applications related to quantum computing. So I hope everybody has now managed to join. Bit of housekeeping first, if we go to the next slide. And
Right, so the first message is to the speakers, I guess. So in here, we recommend that actually, if you have a message to send us, use the chat function rather than raising your hand. And we prefer actually, if you have any questions to the speakers, please use the Q&A function of the Zoom. The session will include time for Q&As after the presentation itself. And you can also vote for questions to upvote them. And after the conference, a video of the session will be available. We will communicate dates via the OR's website. So let's see. So how are we doing with the participants?
Hello. I'm zooming in a bit. Can everybody hear me?
Right. Hi, Kenneth. We can hear you.
Okay, thank you. Good. Shall I start sharing my screen? Or?
Yeah, in the meantime, let me just make a brief introduction. So Kenneth Sörensen is with us for the first talk. He's a professor of the Faculty of Applied Economics at the University of Antwerp. He is the founder and current coordinator of the Association of European Operational Research Societies working group on metaheuristics. And Kenneth currently is the president of the Belgian Operational Research Society. He's also the associate editor of the Journal of Heuristics, the International Transactions in Operational Research, and for OR, the quarterly journal of French, Italian, and Belgian Operational Research Societies. And we really look forward to his talk, solving very large vehicle routing problems with the help of machine learning. So over to you, Kenneth.
Okay, thank you very much. I assume you can see my screen now? Okay, I don't hear anything, so I assume that's a yes. Before I start, I have to give a lot of the credit for this work to Florian Arnold. He's a former PhD student of mine who now has unfortunately moved to industry. Well, not unfortunately, but he's moved to industry, and he did most, if not all, of the dirty work here, implementing the heuristic, testing it, and also many of the ideas are his, at least partially. So a lot of the credit goes to Florian here. Just to set
Kenneth, we cannot see your slides. Could you share it again?
Okay. Okay. Now? You can see that? Yeah? Okay.
We can see it now.
Okay, thank you very much. So just to set the scene, I'm talking about the capacitated vehicle routing problem, one of the most well-known and most researched problems in the whole of operations research, where we have a depot and a set of vehicles that all start and end at the depot, and the vehicles have a certain capacity, and they need to visit a set of customers where you know the demand of. So the aim of the vehicle routing problem is to minimize the total distance that you travel using all of your vehicles. You need to visit all customers, and you cannot exceed the capacity of the vehicle. So a vehicle cannot hold more customer demand than its capacity. As I said, it's one of the most researched vehicle routing problems, or problems in the whole of operations research. Thousands of new papers appear every year on this problem, but it also has a lot of practical relevance. A lot of the logistics planning softwares, like the one you see here, actually have an underlying vehicle routing problem, even though it's a lot more rich, has things like time windows and pickup and delivery and graphical user interfaces, etc. But underlying this is a powerful algorithm to solve vehicle routing problem. So vehicle routing problem is very important in theory and also in practice. Where are we in terms of state of the art? Well, a lot of algorithms exist for the vehicle routing problem. Some of them very fast, some of them very powerful, able to get really high quality solutions. Many of them equivalent. I don't know if you can see my mouse pointer, but I'm basically touching the efficient frontier in this chart here with algorithms that either have a very small gap, like these ones, a gap to the best known solution, or a very small computing time like these algorithms here. And there's a few that are balancing computing time and optimization power. So there's a lot of algorithms, but the literature seems to be stuck, or stuck maybe is not the correct word to say, not really interested in solving anything larger than 1,000 customer vehicle routing problems. Those are called very large scale vehicle routing problems, and there's a couple of contributions on how to solve those. But nobody seems to be really interested in solving much larger problems, even though such problems exist in practice. And even though we can do a lot, or we might benefit from solving much larger problems by being able to solve smaller problems much more efficiently. So the aim when we set out to do this research was the question, can we go further? Can we solve much larger vehicle routing problems in a reasonable computing time? So if you look at this chart, you see two of the current best vehicle routing algorithms. One is an iterated local search, and the other is a hybrid genetic search algorithm. And as you see, when the instance size grows, computing time grows as well, and seems to go more or less like a quadratic function, which means that if you arrive at around 1,000 customers, these algorithms need like 600 minutes, 800 minutes. That's a whole day of calculating time. So it's not feasible to just extend the running time of these algorithms to solve problems of, let's say, 10,000 customers or 20,000 customers. So the question is, can we solve 10 or 20,000 or even larger customers, instances of the vehicle routing problem with that many customers? This one is a real-life example of the Belgian Post Service, who does about 30,000 parcel deliveries per day. So the question is, can we solve a vehicle routing problem with that many customers, 30,000? So when we developed our heuristic for this problem, we set out with a set of, I'd say, fresh ideas, which differed from what is typically done in the literature. In the literature, you typically see now many algorithms for the vehicle routing problem that basically use every possible local search operator known to mankind, right? To-opt, or-opt, replace, things like that. All of them are basically put in the algorithm, and then if it doesn't help, it doesn't hurt, seems to be the guiding principle for those algorithms. So what we did was something different. So rather than using as many possible operators as we could, we used a small set of powerful operators. We didn't invent them ourselves, we used them from the literature. Powerful operators that are complementary, that try to not do each other's job. I'll show you what I mean by that on the next slide. Then we used some data mining, some machine learning to learn the properties of good solutions, and so that we could use this knowledge in the way our heuristics work. And then finally, we used basically what's heavy heuristic pruning, focusing the power of these operators of the heuristic to make it a lot more efficient, so it would be able to solve much larger problems. In this talk, I'm going to talk about, or I'm going to focus on step number 2, in which we use some machine learning and data mining to learn the properties of good solutions in order to make more efficient heuristics. But step 1, or idea 1, was to have a heuristic based on a set of powerful but complementary local search operators. What we did was this. If we have one route to optimize, we use the Lin-Kernighan heuristic. Lin-Kernighan is a whole family of very powerful heuristics for the traveling salesperson problem. But if you have one route in a very large vehicle routing problem, it is essentially a traveling salesperson problem, which can be solved using the Lin-Kernighan heuristic. If we wanted to optimize more than one route, 2 routes, we used cross-exchange. Cross-exchange essentially tries to replace one contiguous part of route 1 with one contiguous part of route 2. It swaps a whole set of customers from route 1 with a whole set of customers from route 2 and tries to create 2 new routes that together are shorter than the first. This is a rather powerful heuristic, but it's also rather computationally expensive, so you have to make it more efficient. And for more than 2 routes, we use the relocation chain, which is some sort of an ejection chain, something which one of our next speakers actually invented, let's say, where in one route you push out a customer, which is then inserted in a second route, which in turn makes this route too large, and then you push out another customer in this route and try to insert it in a third route, and this process can go on, and at the end you hopefully have some more efficient routes. So 3 different heuristics, all of them powerful, expensive computationally, but also complementary, in the sense that they don't try to do each other's work. And now the second idea was, can we learn something about what a good solution is? How can we guide those heuristics to focus on things that will actually make the solution better? Can we learn something about what constitutes a good solution so we can use that in our heuristics? In the literature, you often find quotes like, you can make use of any problem-specific information that you may have, or you can incorporate as much problem-specific information as you're willing to put into the heuristic, etc. The question is, what do we mean by that? What is this problem-specific information that you can use in your heuristic? In a traveling salesperson problem, for example, we know that edge crossings are unwanted. Like if you see 2 edges that cross, then you can always simply make that a better solution by untangling those edges. But for vehicle routing problems, that property doesn't hold. It's not always a bad thing to have crossing edges, but other than that, there is very little problem-specific information known about the vehicle routing problem. Now, how did we try to get that problem-specific information? That's basically the core of this research. So you have 2 solutions here. The one on the left is a very good solution, 0.14% above the best known solution in terms of total length. And the right solution is not such a great solution because it's more than 2% above the best known solution. So what's the difference between those 2 except for their objective function value? So is there a relationship between the solution attributes, the characteristics of those 2 solutions that we can tie to the solution quality? If I put it in a simple way, can we tell whether a solution is good or not without actually looking at its objective function value? Okay, so is there anything about the properties of this solution that we can measure that tells us that the left solution is a good solution and the right solution is not such a good solution. How did we try to get that knowledge? Well, we started from random instances, and for each random instance, we generated a near optimal solution, one which we knew was very close to optimal, and a non-optimal solution for which we knew this is quite far from optimal. And then we calculated for both the near optimal and the non-optimal solution a set of solution characteristics. How many intersections, how many edge crossings does this solution have? What's the average width of this solution? What's the average number of customers per route, etc.? Things like that. Many different solution properties that were not related directly to the objective function value. So, and then we trained a machine learning algorithm to see whether it could predict, based only on these solution attributes or solution characteristics, whether the solution which had these attributes was near optimal, O, or non-optimal, N. So, and based on that, we extracted some rules that gave us some interesting information about what a good solution looks like, except for the fact that it has a good objective function value. Okay, I hope that's clear. So how did we generate those solutions? We use a bit of bootstrapping here. We use our own heuristic, which is quite powerful, has a very small gap on a famous set of instances to generate the near optimal solutions. And for the non-optimal solutions, we actually used two heuristics. One is a weak version of our own heuristic. So we run our heuristic on the instance, and when it reaches a solution which is 4% over the best known solution, we say, okay, stop, this is a poor solution. Same for a 2% gap solution. And then secondly, we also use a second heuristic that we found somewhere in the literature, which produced rather poor solutions, modified Clark and Wright heuristic. Why did we use two heuristics? Well, we wanted to avoid that the classification algorithm would classify solutions based on some properties of the heuristic that was used to solve the instance. So we wanted to make sure that we were seeing the properties of a good solution versus a not so good solution, and not some artifact of the heuristic that was used to find that not so good solution. So that's why we used two heuristics. What kind of metrics or characteristics did we measure? Well, here you see a few of them: the number of intersections, number of times that an edge crosses, the length of the longest edge in routes, the average longest edge, standard deviation of the longest edges in the routes, the length of the edges connecting customers to the depot, the distance between the centers of gravity of the different routes, how well spread out are these routes in the plane, in the area that you're serving, how many customers are there per route, what's the standard deviation here, what's the average number of customers, etc. So all sorts of properties that might influence the solution quality. We don't know yet whether it does, whether they do, but we put as many of those in the algorithm as we could. And of course, this is problem specific. This is not something you can repeat with a different problem. You need some creativity to come up with these different characteristics. The depth of a route, so what's the distance from the depot to the farthest customer in the route. And then things related to how wide the routes are. Let's say how wide do the routes fan out in the Euclidean space that you're serving. The width is, if you would draw a line through the depot and let's say the center of gravity, the average coordinate of the customers in the route, if you would draw a line through those 2 points, then how far away are the customers in the route from that line? Right? So it's measured by the width of the route, the distance between the two furthest customers in the route, how big is the angle between those two customers, and how compact is the route, as more like the average distance of the customers in the route to that line that goes through the center of gravity of the route. Okay, so we put all of those in a support vector machine learning algorithm. I'm not an expert on machine learning algorithms, but essentially you have two clouds of points in this space of characteristics. Let's say that the blue circles here are the non-optimal solutions, and the red squares are the near-optimal solutions. Then the support vector machine tries to come up with a hyperplane that best separates those two clouds from each other. Okay, and that gives you some information on how well you can separate those two clouds. So then if you have a point which is on one side of the hyperplane, if it's on the blue side of the hyperplane, it would predict that the solution is not optimal. If it's on the red side of the hyperplane, it would predict that the solution is optimal. Okay, so how well is that support vector machine able to predict the quality of the solutions? So without looking at the objective function at all, so it's only based on these solution characteristics. And I'm immediately going into the lower right corner here. So if you're 4% from optimal, and well, these are the largest test instances, even though they're still pretty small, the largest instances that we generated data for. Well, then the support vector machine is able to classify around 90% of the solutions correctly as either non-optimal or near-optimal, which really surprised us. So based only on things like how many intersections does this solution have, what's the distance of the customers to the center of gravity of the route, etc., things like that. Based only on that, you can predict with 90% accuracy whether that solution is close to optimal or not close to optimal. And then if you look a bit further, you can investigate what properties actually cause most of this prediction accuracy. And then it turns out, and I'm summarizing this slide a bit, it turns out that these issues or the characteristics related to how wide the edges are, so they tend to contribute the most to the prediction accuracy. So this somehow intuitively seems to be correct, but if you have a line which connects the center of gravity of the route with a depot, then you don't want to have edges that run perpendicular to that line. You want to have edges in a solution that either go to the depot or from the depot, but not edges that don't increase or decrease the distance to the depot. Somehow intuitively, that seems to be correct. That seems to be some kind of lost distance, and these experiments confirm that. So with that information, we were able to say that, well, okay, obviously we don't want to have long edges in our solution, but also we don't want to have wide edges in our solution that cover a lot of distance perpendicular to that line that connects the depot to the center of gravity. So now how does the heuristic work? In total, basically we focus on the worst edge. The worst edge is based on how wide the edge is and how long it is, and we penalize edges. So every bad edge gets its turn to be selected as the worst edge, and then that edge is removed. And then we focus the local search around that removed edge, okay? So that's a third idea that we brought to the table. We could really try to efficiently focus those heuristics on edges that we think are going to be bad. Intuitively, if you have a very, very large weak routing problem, you're going to see customers are connected to close customers, to close neighbors. And if you make a list of customers in order of distance from a certain customer, you don't expect that customer to be connected directly to a customer that is in 1,000 position on that list. That doesn't make any sense. And we see that empirically, like in very good solutions, 95% of the customers are connected to a really close customer that is that is not more than the 50th closest customer. Right? Remember, these are very large instances. And 99% is not connected to a customer that is located more than 100 customers away from this customer, for example. Okay, so intuitively that makes sense. And that allows you to really focus the search on customers that are expected to make a difference if you start changing them around. So our heuristic in a nutshell is this. So we create a list of the C nearest nodes for each customer, right? The C nearest customers. We remove the worst edge based on that penalization criterion, which is based on the width and the cost of the edge. And then we apply those local search operators that I showed you in the beginning, but we restrict ourselves to nodes not more than C nodes removed from A or B. So the nodes that are within the C closest nodes from either node A or node B. And then you basically get a constant time local search operator. Okay, because this one, the worst edge is selected outside of the local search operator, and these are also a constant number of changes that you need to check. So that gives you a constant time search operator. Of course, you need to do some tweaking with the parameter C. It seems that 100, for example, was not enough. Worse solutions, or at least a worse convergence. 15 is the 15 closest customers, that was not enough, right? And something like 30 or 50 seem to perform well in terms of convergence of the heuristic. So time for some results. So you remember this slide, one of my first slides. It's time to put our heuristic on this slide, and you can see our heuristic has a much nicer performance in terms of increase in computing time for large size instances. So this means that we can solve, using this heuristic, much larger instances of the vehicle routing problem. If you put our heuristic, different running times of our heuristic on the list of best performing heuristics for the VRP in terms of gap to the best known solution and computation time, we see that we are consistently on the Pareto frontier, even though some solutions or solution methods are even faster, or some achieve even better solutions than we do. We are performing very well in terms of solution quality versus computation time. So numbers too many for you to see, but we either have a similar performance much faster than the best heuristic existing for very large instances, or we are a similar computation time, we are much better than the best heuristic for these very large instances. Okay, here are some pictures, which say more than 1,000 words. I don't know, I'm not sure in this case if you can see anything in this spaghetti, but these are some 10,000 customer instances. And this is the 30,000 customer instance that I referred to in the beginning. This is the region where I live, Flanders. This is my home city, Antwerp. This is Brussels, capital of Europe. And here you see a zoom on that region of Brussels. So you really see how many customers we're visiting there. It's really, yeah, I really like this picture. So to conclude, I think we've come up with a modern way of designing heuristics using powerful complementary local search heuristics. Make them efficient using knowledge on what a good solution looks like, even if you don't know the objective function value, and make those local search heuristics a lot more efficient using heavy pruning to avoid doing unnecessary calculations. Voila, if you want to try, you can download this on the website that Florian created. Here is Florian, by the way, routings-solver.com. You can download an executable version, which is also able to solve some related problems like location routing problem and other problems. Okay, thank you very much. That was it. I hope I more or less stuck to my timing.
Yeah, thanks, Kenneth. So we have a couple of questions here, but we don't have much time left. So I'll just pick one. What does happen if solution properties are conflicting? Was there any situation like that?
Yeah, you hope that the machine learning algorithm catches that it filters those out. It also takes a little bit of let's say pruning of the machine learning algorithm. It's not as simple as just throwing everything at the machine learning algorithm and then hoping that it automatically comes up with the perfect solution. You need a bit of tweaking here and there, perhaps remove some of those conflicting
problem. Yeah, so I'll just take one, and then I think that should be sufficient for the questions. So presumably by creating the attributes, you already had an intuition that would be helpful, and the machine learning just confirmed your intuition. So did you really need the machine learning?
Yeah, good question. Yeah, well, maybe this is true for this simple vehicle routing problem, but I guess for many other problems, there is no such intuition. So there, it might be even more useful to use the machine learning. It's true, we already had this intuition, but I wasn't sure that my intuition was true. That's one answer. And secondly, the technique is more versatile, and I think you can also, and maybe even better, apply it when you don't have that intuition. Then yeah, maybe better there.
Okay, thanks. Yeah. Thanks, Kenneth, for accepting our invite and for an interesting talk. Thank you very much. Over to you, Andrew, Friend, Udo, and Pierre.
Okay, yeah, I'm not sure if you can hear me. I can't start the video at the moment, but so moving on to the second talk now. Very happy to welcome a group of 3 speakers talking together from University of Colorado. So we've got Fred Glover, Gary Kochenberger, and Udo. Fred hardly needs any introduction, of course. A very, very well-known name in the area of metaheuristics. The name he created. Many deep and important contributions to the area, of course, prominently taboo search and many others. Gary served as interim dean of business school. His research focuses on new modeling and solution techniques. He's written several books and published in numerous journals, Management Science, Operation Research, and eJAW. Udo is in the business analytics at the Business School of University of Colorado. Her research interest is in large-scale, data-driven mathematical optimization. And so with that, we'll happily hand over to the Colorado team with their talk, as you see on the slide. So over to you.
Thank you very much, Andrew. Thanks for a great introduction. Thanks everyone for attending our talk. Our topic today is called New Metaheuristic Applications Related to Hot Topic Quantum Computing. This is talk by our team, Fred Glover, Gary Kochenberger, and me. From now, I'm handing to our team leader, Fred Glover, to start the talk.
Thank you, I think we can move on from our first slide to that you see here. Let's advance to the next one. Very good. Our background here, that's good, stop there. Our background here is that we're using what we call quantum bridge analytics. The idea is that we're developing new methods that can be considered classical and quantum computing combined. And the approach is to use these combined types of methods to give us a basis for future applications that will be effective when the quantum computing area eventually comes online and is powerful enough to make a big difference. Very good. Next slide, please. We're motivated a great deal by a consensus study by the National Academies of Sciences, Engineering, and Medicine, which was just released last year, which says that quantum computing is in its infancy right now, and that we need the hybrid quantum and classical techniques to support adoption as the quantum computing matures. And what we're doing is to pursue this, and we're using a special model called the QUBO model, which is sort of an intersection model between quantum and classical world for solving a lot of application optimization problems. And this is something that Gary is going to elaborate on and tell you about our very, very welcome successes in this area. Okay, next. Next slide, please. All right, then I'm handing off to Gary here. Gary Kochenberger will take up.
Thank you, Fred, and thank you. Can you hear me all right now? Okay. Well, as Fred mentioned, the connection between the quantum computing world and some of the things that we've been working on in the classical optimization world is this QUBO model. And it's very easy to represent the QUBO model. It's simply this unconstrained quadratic binary problem as depicted there. So you want to optimize X transpose QX, where X is a vector of binary variables and Q is a symmetric matrix that contains all the data of the problem. And we'll talk more about this on the next slide, many organizations today, particularly those coming from the quantum world, are heavily involved in carrying out research and application developments of this very special QUBO model. And by the way, that connection between that QUBO represents between the conventional combinatorial world and the quantum combinatorial world derives from the equivalency between the QUBO model and the famous Ising spin glass model in physics. So you see companies like D-Wave and Fujitsu, Toshiba, and all the others listed there are heavily involved in developing applications of this QUBO model so that they can take advantage of the power of quantum computing, which we all believe is coming. At the same time, the conventional solvers are getting better and better and are very powerful as well. So a lot of the research that's going on today has to do with comparing conventional solvers for the QUBO model and the quantum solvers for the QUBO model. We've been doing this type of work for some time and have collaborations with several of these companies, and including the National Lab at Los Alamos, where we have some collaborations going on. But you can see from this slide that lots of the major organizations around the world are very interested in this QUBO model, and there's a lot of research and application development going on. You want to advance, please? One of the really remarkable features of this QUBO model is its ability to serve as what we call a unifying framework for many, many important types of combinatorial problems. And the way this works is you take your classically formulated problem and impose the constraints in an alternative to the traditional manner by including the constraints as quadratic penalties in the objective function. that transformation is very easy to implement, and it takes a classically formulated problem and turns it into a QUBO model. In recent years, lots of applications of this transformed QUBO model have been reported in the literature. And on this slide, we count some of these applications that are found in the literature. They range from financial services applications as depicted there, applications in transportation as shown there, manufacturing, and we'll see on the next slide that these applications that are reported by, primarily these are applications reported by firms like Fujitsu and D-Wave and others that are working in the national labs, working on finding applications for quantum computing. We've worked on some of these applications, but as you'll see on the next slide, in terms of classical combinatorial problems, we've worked on all of these applications that are listed here, from graph coloring, knapsack problems, max cut problems, and so forth. And the purpose of this slide and the previous two slides is just to highlight the breadth of applicability of this QUBO model, that very special model that stands at the intersection of some classical combinatorial approaches and some quantum approaches. Can you advance? One of the things we've been working on recently is what we call QUBO-Plus models. So go ahead and advance you. These are models that augment kind of the standard QUBO representation by holding out a few special constraints rather than folding them into the objective function to produce a pure QUBO model. And we've modified our QUBO solvers to be able to accommodate some of these special constraints that we might want to hold out. Go ahead, one more, you. So in contrast to the pure QUBO models, in the QUBO-Plus models, as I said a moment ago, we hold out a few constraints. And what we found is that in certain applications, there are good computational reasons for doing this, and also for the notion of model transparency. You might want to hold out one or two special constraints rather than folding them into the objective function, producing in that manner a pure QUBO model. Go ahead, you. So some of the special cases that we've been experimenting with would include these, what we call QUBO covering problems. These are models that could be converted into a pure QUBO model, but we find that there's some advantage to holding out very special constraints, like the requiring the sum of the variables to be greater than or equal to a specified constant, QUBO models combining packing and covering constraints, QUBO knapsack problems, both single and multiple knapsack problems, and what we call generalized covering QUBO problems, those situations where you might want to require a weighted sum of the variables to be greater than or equal to some specific amount. Let me highlight that one particular really important application here is the situation where you have a QUBO model that's augmented by a single cardinality constraint, requiring the sum of the variables, say, perhaps to be equal to some specified constant. That particular application shows up in many settings, including portfolio models, where you might want to have you might start out with a set of, say, 1,000 assets, and you might want to choose the portfolio that has exactly 100 assets chosen. That's the type of situation. Go ahead, you. Some of the technical advances that we've been working on include the ones I'm going to speak about right now. Pre-processing methods. We've been working a lot on developing new pre-processing methods for the QUBO model that identifies a priori variables that can be set to either 0 or 1. And of course, this has the obvious advantage of enabling you to reduce the size of the problem and possibly solve it more efficiently. And the motivation for this comes from the fact that these applications involving QUBO and QUBO-Plus models are scaling up in size substantially. And so we're motivated to devise methods, both the solvers in and of themselves and pre-processing methods that can enable us to solve much larger problems. We'll see on another slide where we're also working on partitioning methods to enable us to solve large problems. That's the slide we have here. And I might mention we're also working on GPU implementations of our QUBO solver, which early experience suggests that this GPU can deliver substantial improvements in performance. And as I mentioned previously, the partitioning work, these are all areas of advancement, pre-processing, GPU, and partitioning, designed to enable us to solve much larger problems than we're solving today. Having said that, I'll show you in a moment some computational experience which underlies the fact that we can today solve some very, very large QUBO problems. We'll come to that in just a moment. What I'd like to do now over the next couple of minutes is highlight some of the computational experience we have, showing some comparisons with both some exact solvers and some quantum solvers. And the quantum solver we had access to is the D-Wave solver. So this little table contains some computational experience with some portfolio problems. And these are small problems with 100 assets up to 500 assets. It turns out that these problems were pretty easy to solve. Both the D-Wave solver and our conventional solver, AlphaQUBO, were able to solve these problems without any difficulty. The big difference is that our conventional metaheuristic, AlphaQUBO, was able to arrive at these solutions much more readily, about 700 times faster than the D-Wave QUBO solver. Go ahead, you. This is an example showing a comparison of our conventional QUBO solver with the exact method of CPLEX. And of course, one has to always be careful comparing an exact method to a metaheuristic. We expect metaheuristics to perform well on really complicated problems. But CPLEX has improved an awful lot, and it's a good benchmark to have in mind. But one does need to consider that we're comparing an exact method with a heuristic method. But notice in these problems, these are all maximization problems going up to 20,000 variables. The largest of these, and I think we ran some of these for 48 hours. CPLEX was not able to provide solutions. Our heuristic was able to provide very high quality solutions very quickly, as we see on the right-hand side of this table. I think on the next couple of tables, we have more comparisons with D-Wave. Do you want to go ahead? Yeah. Here's a little table that shows some comparisons with our conventional QUBO solver and the D-Wave LEAP system, which I think is their second generation hybrid method. So on the smaller problems, D-Wave did very well. You can see that the conventional solver, our AlphaQUBO metaheuristic, did very well and has a much better performance in terms of both solution and time to best. And as these problems got larger, as they scaled up, as shown on the last couple of rows of this table, D-Wave was not able to return solutions at all. AlphaQUBO didn't have much difficulty with these problems. You want to go ahead? This table and the next two tables represents a study that we just completed about a week ago And this has to do with solving set partitioning problems. And in this table, we have a comparison with CPLEX, with the D-Wave LEAP system, and with our conventional solver, Alpha QUBO. This first of these three tables are problems of modest size. They go from 6,000 variables up to 8,000 variables. And we can see from this table that CPLEX solve these problems without a whole lot of difficulty, the first few of these anyway. And D-Wave was not, so these problems that are highlighted, the solutions that are highlighted in yellow in the CPLEX objective function column, those are all proven optimal solutions. The last entry of that column was the best solution CPLEX could produce. And I think we let these run for 5 or 6 hours. If you notice under the D-Wave section of this table, D-Wave did pretty well, but was not able to find the optimal solution to any of these problems. And our conventional solver, Alpha QUBO, very quickly found the optimal solution to all of these problems. It turns out, can you go to the next slide? Here's a slide of some additional set partitioning problems that we worked on. And these vary from 10,000 variables up to 40,000 variables as depicted there. D-Wave couldn't produce solutions. The version of D-Wave that is available today has a limit of 10,000 variables. It was not able to solve the 10,000 variable problems in this particular table. You'll see in yellow there that CPLEX was able to solve many of them. And I think these ran for 5 or 6 hours. And you'll see on the right, the two most columns on the right give the results from our conventional solver, Alpha QUBO. These are very large, these 40 variable problems are considered to be very large QUBO problems. But we went even beyond that as shown in the next slide. So if you'll advance one more time. These are additional set partitioning problems that go from 50,000 variables up to 100,000 variables. So again, to make sure that everyone understands what we did here, we took these very large set partitioning problems, and we have two models. We have the standard linear set partitioning model, and that's the model that's solved by CPLEX. And then we have the QUBO equivalent model, and that's the model that's solved by Alpha QUBO. And these models ran again for, I think it was 6 hours. When the runs terminate, CPLEX gives you the best solution they found within that time. And you can see that these problems were difficult for CPLEX. It was not able to prove optimality in any of these. And you can see in the rightmost columns, Alpha QUBO produced very high quality solutions in modest computational times. These QUBO models with up to 100,000 variables, as far as we know, are the largest QUBO models ever reported in the literature or at a conference like this. And again, we just completed these runs last week. You want to go ahead? We have, by the way, I presume everyone will be getting these slides. If there's any difficulty with that, please contact us and we'll send them. We also have these references for you. We have a tutorial on formulating and using QUBO models. And then we have some information about our solver at those websites depicted there. So we're really excited about this work, and in particular, the set partitioning study that we're just finished, and we highlighted some of the results from that study. Those results demonstrate clearly that the QUBO model is much more than a novelty. I mean, we've known that for some time, and the list of applications that we shared with you there provide further testimony to the applicability of the QUBO model, but the ability to solve these large-scale set partitioning problems, I think, really adds further evidence, really important evidence, that the QUBO model is capable of being a modeling and solution vehicle for very large-scale combinatorial problems. Thank you very much. I think it was, yeah.
Okay, thank you very much as well. Excellent talk, very interesting. We're running out of time very, very soon, I think. But a question from the Q&A, is this related to the Fujitsu digital annealer, or are you familiar with it?
Yes, absolutely. We didn't have access to the Fujitsu solver. We'd love to get access and include that in our study. But yes, that solver is also designed to solve the QUBO model. Yeah.
And
yeah.
I'd like to say something here, that although we don't directly have access ourselves, we do have experience through a group that does have access, and we solve problems for them, and we have compared our solutions, and we discover that in a very short time we're getting better solutions than the digital annealer gets when it runs a very long time. So, and by the way, when Gary refers to ours as a conventional solver, the solver itself is not conventional. It runs on conventional machines.
Yeah, that's right. Yeah, that's a good clarification. Yeah, our solver is a modern metaheuristic method built around things like taboo search, path relinking, and the like. Yeah.
Okay. Okay, I think we're about to run out of time because I think they're quite strict on time. So thank you again for the very interesting talk about quantum, way of the future, we imagine. And so thank you again for excellent talk, and thank you, Kenneth, as well from before, again, for a very interesting talk on VRP. And I believe that ends the session now with, oh, really a minute early, but so Ender, are you online?
Yes, in a virtual environment, maybe we should just, you know, if you like to do this, you can turn on the videos and we can clip our speakers. So thank you very much for all these talks.
Yes, thank you very much. It's difficult in a virtual environment, but virtual clapping. And this is where we'd all go off for coffee and discuss it in detail, right? Unfortunately, we can't. So thank everyone again for attending, and thanks particularly the speakers again for giving some excellent talks. Thank you.
Bye, thanks.
Bye. Thanks.